Now the third is, that is a numerical based on the first order reaction. And okay, so it's a important part of the with respect to the numericals. The first order reaction where we had learned that the rate of reaction depends on the concentration of the single reactant with the power 1. Now when we are talking about the first order reaction, the reaction generally asks on the two factor. The one is the rate constant, that is K, and the second it is asked on the T half-life period. And for both we have a formula. For K we have a formula, that is K is equal to 2.303 upon T log to the base 10 molar concentration of A naught upon AT, where A naught is called initial concentration of reactant and AT, it is called the concentration of reactant after time T. So A naught, it is the initial concentration of reactant, and the AT is the concentration of reactant after time T. Now instead of concentration, sometimes they give the questions on the pressure, sometimes they give the questions on the volume. So first we will cover with this formula, and then we will learn about those formulas also. And then we have the half-life period, T half. The formula is 0.693 upon K. For first order reaction, the half-life period does not depend upon the initial concentration, and hence the formula does not involve any A naught term, the half-life formula. Okay, now when the question comes on the half-life period, then we had learned one more formula, that is AT is equal to the concentration of reactant left after time T is equal to A0 upon 2 raised to n, where n stand for the number of half-life period. It doesn't represent order of reaction, it is number of half-life period. Again, while solving MCQs, the very important formula. Okay, now based on the half-life period, we have a different method to solve. Now while talking about the half-life period, suppose some terms to be kept in the mind. For example, suppose if I have the 100 molar reactant in the beginning, then after one half-life, I will say that 50 molar reactant is left. After next half-life, I will say that 25 molar reactant will be left. After next half-life, 12.5 will be left. And after next half-life, I can say that 6.25 will be left. These are the left amount. Now the amount which is consumed. So I can say if the 50 molar is left, then consumed amount is also 50. Taken amount were 100. If 25 is left, that is the consumed amount is going to be 75. Out of 100, 25 is left, means 75 is consumed. If 12.5 is left, it means the consumed amount is going to be 87.5. If 6.25 is left, it means consumed amount is going to be 93.75. Now from this, I can say that the time required for 50% is T halves. Time required for the 50% reactant to consume is T half. That is the same. Time required for the consumption of 75% of the reactant is 75% to for the consumption of the 25 is left, means 75% is consumed. So for the consumption of 75%, how much half-life is needed? 2 half-life. So I can say it's a 2 half-life. Sometimes they give in the question they give the rate constant or they give the half-life, and the question is asked that calculate how much time is needed for the consumption of 75. So it's an important relation again. For the consumption of 87.5%, 87.5%, I can say it's a 12 point, how many half-life is needed? Then 1, 2 and 3. After third half-life, 87.5 will be left, 3 half-life. And similarly so on, that is for 93.75% reactant to consumed. How much half-life is, again I can say 4 half-life. So again, it is a very important thing. Means directly, if I know this relation, I can write or I can solve mini numericals without wasting time. So this is again a very important one. So we have a question. The half-life period of a reaction is 140 seconds. How much of the reactant is left after 560 seconds? So the half-life period is 140 and the total time is given as a 560. So here I can say 560 seconds is equal to 4 into 140. That is, I can say 4 half-life. So ultimately they wanted to know the amount of reactant left after 4 half-life. So we have two different methods for solving this. The number one, I can say we just did a formula. Suppose here AT is equal to A0 upon 2 raised to n, which is equal to, initial amount is not given. They want the amount left after 4 half-life, that is after 560 seconds, that is 80 we have to calculate. So A0 upon 2 raised to n. Now A0, it's not given, so consider it as a 1 upon 2 raised to n. 2 raised to n means 2 raised to number of half-life. So number of half-life is how much? 4. So 2 raised to 4, that is 1 upon 2 raised to 4 is 16. So this is the answer. That after 4 half-life, how much reactant will be left? 1 upon 16. The alternate method which we can use, it is, I can say initially let this is 1. After 1 half-life, that is after 140 seconds, it will become 1 by 2. After next half-life, that is second half-life, it will reduces to half. Half of 1 by 2 is 1 by 4. After next half-life, it will again reduces to half and it will become 1 by 8. And after next half-life, that is we are total considering 4 half-life. So after next half-life, it will become 1 by 16. So by this method or by this method, the answer is going to be same. The next, the T0.75 of a first order reaction is 138.6 seconds. Calculate specific reaction rate. Specific reaction rate means they wanted to know about K. So we have to calculate K. What is given here? Here the given term is the T half T0.75. It's given as 138.6. T0.75 means I can say it is in the fraction form given. If I am considering the percentage, then it is T75. T75, then I can say T0.75 is nothing but 2 times of T0.5, that is T half. So I can say this value is 138.6, right, is equal to 2 T half. 0.5 means I can write half. So T half is equal to, here I can say 138.6 divided by 2, which is going to be 2 6 are 12, T 2 9s are, and then 3s are. This much seconds. Okay. Now I got T half. After that I have to calculate specific reaction rate. If you know the specific T half, then I can calculate specific reaction rate, that is a rate constant also. So rate constant, that is K is equal to, we have formula 0.693 upon T half. So it is equal to 0.693 upon T half is 69.3. That is equal to, I can say 0.01 first order reaction it is. So it is going to be per time, that is per second. So this is the answer.